Equilibrium and equilibrium constants going to be the topic in this first lesson in a whole chapter on chemical equilibrium. And next lesson, we'll talk about Le Chatelier's principle. We'll then move on to some equilibrium calculations. And then we'll use those equilibrium calculations to revisit acids and bases. We'll talk about weak acids and bases. And then finally, we'll have a whole lesson on solubility equilibria. Now, in this lesson, we're going to define what chemical equilibrium is, and we'll also define what's known as the equilibrium constant, and we'll figure out what exactly it tells us. Now, this lesson is part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. All right, so equilibrium. When we talk about equilibrium in a chemistry context, we're talking about what's known as a dynamic equilibrium. So there's really two types of equilibrium. We talk about static equilibrium and dynamic equilibrium. And a static equilibrium looks like this, as in nothing's happening. That's not what we're talking about in chemistry, though. In chemistry, we talk about a dynamic equilibrium. When you've got a chemical reaction so that has reached its end point, if you will. Well, most chemical reactions do reach an end point, but they don't necessarily go to completion, where all the reactants are converted into all the products. That's not typical of most chemical reactions, and so you make it some intermediate point where you've got some leftover reactants, you've now formed some products, but you've got a mixture of both in your solution. This is different points and different relative amounts of reactants and products for different reactions, and the equilibrium constant will be something that allows us to quantify that point. But this dynamic equilibrium, when you reach this point where your reactant concentrations and product concentrations are no longer changing, that is when you've reached equilibrium. And it's not that the reaction is stopped, it's just that it's reacting in both directions at exactly the same rate. So every reactant that turns into a product, there's a product that turns back into a reactant. And so overall, your concentrations are no longer changing. And that is what we mean by dynamic equilibrium. The key is that the reaction is not stopped, it's just happening in both directions at the same rate. Notice this does not mean that you have equal amounts of reactants and products, it just means the reaction is going in equal rates in opposite directions. So the forward rate and the reverse rate of the reaction are equal. So it's the rates that are equal, not necessarily the concentration. So keep that in mind. Big distinction, big common misconception. All right, so we're going to take a look at a reaction here. And in this case, I've got a concentration of A and a concentration of B graphed over time. And we're going to use this to accomplish a couple of things. One, we're going to figure out what this reaction is. And then two, once we figure out the stoichiometry here, we're going to figure out what we're going to be calling the equilibrium constant in a minute here as well. So in this case, if we look, which of these has a concentration that is decreasing? So in this case, that's A. Its concentration's going down over time. So that is our reactant in this case. So, and then who's got a concentration that's going up? Well, that's B. And so B is the product in this reaction. And so here I've got A going to B, but that's not going to be good enough here. So because it's not a 1-to-1 ratio, and you can tell not by where they end up or anything of that sort, but by how much they change by. So if you look at this, A starts out at a concentration of 0.7 molar, ends up at a concentration of 0.3 molar. And so you could figure out that the change in the concentration of A is negative 0.4 molar. That's how much it's gone down by. All right, so whereas the change in B, it starts at 0 and goes up to 0.2 molar. And so the change in the concentration of B has been simply just 0.2 molar. And so what we can see is that A has gone down more than B has gone up. In fact, A has gone down twice as much as B has gone up. And the reason is due to the stoichiometry. So we've got to put a 2 there in front of the A, because for every B we produce, we've lost twice as many A. That's what these changes in concentrations are really going to tell us. That we're getting the stoichiometry, that mole-to-mole ratio. All right. So now that we've got that, now we've got to define what we call this equilibrium constant. Now, notice these are all given in molarity. So, and in this case, that means we're doing an aqueous reaction. A and B are both aqueous. They're dissolved in water here. It's why they have molarities. And so the equilibrium constant is turned out as the ratio of products to reactants at equilibrium. And so in this case, we often define what's called KEQ, which I'll leave generic for just a second. And so in this case, the brackets here mean molar concentration of. And so in this case, it's products over reactants. And so it's concentration of B over concentration of A, but there's a little more to it than that. It turns out we use the coefficients in the balanced reaction as exponents. And so here there's only one B, and so it's B to the first power. Well, anything to the first power is itself, so we don't write it in. But here it's going to be over A squared as well. Now, one thing to note, we don't typically write this in, we just expect you to know this. So it turns out it's the concentration of B at equilibrium and the concentration of A at equilibrium in order to be called this equilibrium constant. So, but we don't typically put that little subscript there to show you that it's the concentration of B at equilibrium and the concentration of A at equilibrium. We just expect you to know that. So don't expect that to be written. We just expect you to know that it's not, you can't just pick the concentration at any old point in time you want to. If it's going to equal the equilibrium constant, it's where you have to pick the point where the concentrations are no longer changing and you've reached equilibrium. And so we can see where that point would be in this particular case. So we can see that the concentrations of A and B are no longer changing way out here. They've gone completely horizontal on the curve. And so that's evidence that the reaction has reached equilibrium. And so in this case, we can see that the concentration of A is 0.3 molar. And so if we want to figure out this equilibrium constant, the numerical value of it, we'd plug that into the formula. So, and then same thing, it turns out with the concentration of B, which is now 0.2 molar once it reaches equilibrium. So now if we pulled out our handy dandy calculator here, so we're going to do 0.2 divided by 0.3 squared, and we're going to get 2.2. If I round it to 2 sig figs here. Put a 0 on there just like the 0 that was there. So 2.2. Now, one thing to note, I left the units off this. So notice this would have units of molarity, and then it would be down here be molarity squared. And it looks like this equilibrium constant would come out with units of molarity. Well, it turns out we don't give you the full definition here. It turns out what they do is every time you plug into a concentration into this formula, you divide it by 1 molar. That way the units fall off. And so equilibrium constants do not have any units. They're completely unitless. So even though it looks like if you keep the molarities on here, then when you plug the numbers in, you might end up with some molarities or something, or 1 over molarity or something for units. But again, the key is we divide every concentration by 1 molar before they ever get plugged into this formula. That's why there's no molarities here. And we don't really spell that out. If you took a more advanced class in college, we might actually spell that out and get pretty rigorous about this and technical and formal. So, but in high school and even freshmen in college, we don't. We just leave it like this and just kind of tell you, hey, no units on that equilibrium constant. Even though it looks like it might, just don't worry about it, no units. So that's where we're going to go here as well. So here the equilibrium constant is 2.2. Now it turns out this equilibrium constant has a utility, and it tells us something about a reaction. So because when a reaction reaches equilibrium, we want to know maybe like, well, are there going to be a lot of reactants, or are there going to be a lot of products, or are there going to be a lot of both, or something of this sort? And so notice it's the ratio of products over reactants. And so the numerical value is going to tell us some things. And so oftentimes we kind of define this like so. We're going to go big or go home first. And so in this case, if your equilibrium constant is a lot bigger than 1. So notice if your ratio is equal to exactly 1, so that would mean that your numerator and your denominator were equal. Okay. So that would mean that you'd have similar amounts of reactants and products. Well, what if your constant's way, way, way bigger than 1? And usually to say way bigger than 1, we mean bigger than 10 to the third, bigger than 1,000. Well, that would mean you have a lot more numerator than denominator in this ratio. You'd have a lot more products than reactants. And when that's the case, we say that the reaction favors the products. Whereas on the other hand, if your equilibrium constant is way smaller than 1, and usually we just kind of arbitrarily pick a numerical cap and say, well, again, k bigger than 1 is bigger than 10 to the third, so k smaller than 1 is smaller than 10 to the negative third, smaller than 0.001. And if that's the case in that ratio, well, for this ratio to come out so small, it means that your numerator has to be a lot bigger. Your denominator's got to be a lot bigger than your numerator. So you'd have to have a lot more reactants than products once you reach equilibrium. And so in this case, when k is way, way smaller than 1, we say that the reaction favors the reactants at equilibrium. So, and then if your equilibrium constant is somewhere in between 10 to the third and 10 to the negative third, so that's when you're going to have both reactants and products. A fair amount of both present at equilibrium. Cool, and so that's the utility of this equilibrium constant. So When I see an equilibrium constant, let's say is like a billion, well, that tells you something. For an equilibrium constant that's a billion, that's a reaction that goes really close to completion and is going to have a ton more products than reactants once we get to equilibrium. Whereas when I see a reaction where an equilibrium constant's like 1.5 times 10 to the negative 12, well, that's a super tiny number, and that's a reaction that favors the reactants. That means there's going to be hardly any products present. It's going to be mostly reactants in your reaction mixture instead. So that's kind of the idea. I guess we'll pick one in the middle as well. So what if I told you you have an equilibrium constant of like 3.2 or 2.2 as the case is here? So, and with an equilibrium constant like that, that means you're going to have a fair amount of both reactants and products. Now, if it's bigger than 1, we might think probably a slight excess of products compared to reactants, but it's not quite so easy because sometimes you get these exponents in here so that are going to throw things off. And so even if you have equal concentrations of reactants and products, well then by necessity, your ratio has to come out to 1, right? Well, not necessarily. I mean, if it was 1 over 1 squared, sure, but what if it's 2 over 2 squared? That's not going to come out to exactly 1. And so that's why we give some leeway here for the middle one. So and say it's in the ballpark of 1, then you're probably going to have a fair amount of both reactants and products. Cool. So we've defined what it means to have a dynamic equilibrium. Forward rate equals the reverse rate. So, but it doesn't mean the concentrations of reactants and products are equal at equilibrium. Does not mean that at all. I mean, it could be true in some random reaction, but it doesn't have to be the case at all. But it's the rates that are equal. We're going to be forming B and unforming A at the same rate. And so oftentimes you're going to see us rewrite this lovely arrow right here. Instead of like the normal reaction arrow, you'll see in this chapter, quite frequently, we'll write it like this. And the truth is, even if you see an arrow written like this, again, most reactions don't actually go to completion. And so an arrow written like this is just kind of our common everyday use chemistry arrow. However, most of the time, it really is this. Even if you see it written like this, just consider, yeah, it probably is going to reach some sort of intermittent equilibrium anyways. Cool, but you're going to see this double arrow right here used pretty ubiquitously this chapter, and that's what we use kind of represent, yes, just kind of make a big point of saying, yes, this reaction is going to equilibrium. At some point, it's going to go in both directions at the same rate when it gets to equilibrium. All right, so this is my favorite reaction for this chapter, and we're going to deal with it quite extensively here, both in this lesson and the next. And, in this case, first thing I want to do is write out an equilibrium constant for this reaction. And so in this case, again, we'll call it KEQ. So it turns out that, in both high school chemistry and in freshman chemistry, we'll use this term KEQ. But if you go a little further than that, you'll find out it's not really proper. And you'll see people using the term KC for concentration more commonly. And we'll contrast that with something else. So I'm going to do that. I'm just going to kind of jump ahead, but you'll see KEQ kind of very generically used, but KC means molar concentrations, and we'll see why that's necessary in just a second. So if we look at this equilibrium constant expression for this reaction, so we're going to get products over reactants, and so we're going to have CO squared, and then it's going to be over the concentration of O2, and then it turns out, though, that carbon's not going to show up in the expression at all. And so what you're going to end up learning is that solids and liquids don't appear in your equilibrium constant expressions typically. So it is typically just gases or aqueous species. And notice when you've got an aqueous species, it's dissolved in water and it spreads out uniformly throughout that water. And if you've got a gaseous species, that gas is spread out uniformly throughout the container. So, but if you've got a solid, say in water, well, that solid's not going to spread out throughout the container. It's just going to go sit in the corner and sit on the bottom of the beaker. It's not uniformly spread out. It doesn't really have a concentration per se in the same regard as something that's actually dissolved in the water. And so it turns out in physical chemistry, which is definitely far beyond this class, but we say that solids and liquids have an activity of 1. So, and that's so far beyond this class, is not funny, but the big thing is we say they have an activity of 1. And so what you'd plug into the expression for them is a 1. Well, anything times 1 or divided by 1 is itself. And so they don't end up having any impact on the equilibrium constant. And that's why we're going to leave them out. So I'm explaining that. It's not the most important thing. I just didn't want to just be like, well, we just leave them out. And you should know that. I just wanted to give you a little bit of the explanation there, but we're going to leave all solids and liquids out of our equilibrium constant expressions. We're only going to put gases and aqueous species. All right, so when you've got a gaseous species in your reaction like this one that shows in your equilibrium constant expression, it turns out there's actually 2 ways to write your equilibrium constant expression. And so you can write it in terms of molar concentrations, and it's still products of reactants, but it turns out you have another option, and we call this other option Kp. And in this case, it's P for pressure, so C for concentration, P for pressure. And it's still the ratio of products to reactants, but now instead of measuring molar concentrations of these gases, we're going to measure the partial pressure of these gases instead and do the exact same ratio though. So again, still products over reactants raised to the power of the coefficients, but using partial pressures instead of molarities. And the numerical value of these two does not necessarily have to be the same. So you might recall with the ideal gas law that PV equals nRT. And if we rearrange this ever so slightly here, so we can see that P equals N over V RT. And notice N over V, N is moles of gas, whatever gas you're talking about, and V is volume, typically in liters. And notice moles over liters is molarity. And so we can come out with an expression where pressure is related to the molarity. And so it turns out they're proportional. If you double the molarity, it would double the pressure, but they're not equal because there's this extra factor RT. And so notice, like if we plugged in, instead of partial pressures here, we plugged in molarity times RT for, both in this expression, the RTs aren't going to cancel because there'd be an RT quantity squared on top, but only a single RT on bottom, and you'd be left with this extra factor of RT in the numerator that doesn't cancel. And so it turns out there's a relationship between Kp and Kc, but they're not necessarily numerically equal. And so the expression we come up with has to factor in those extra RT factors that may appear. So and this is how this expression works here. So it takes into account how many extra RTs you might have either in the numerator or the denominator, where delta N here is the change in the number of moles of gas. And that delta N could be a positive number if you end up with more moles of gas on the reactant side, or it could be a negative number if you end up with fewer moles of gas, a decrease in moles of gas on the product side. So in our case, it's only about the moles of gas. We couldn't care less about the solid. So in this case, we're going from 1 mole of gas to 2 moles of gas. And so it's an increase in the number of moles of gas by 1. And so delta N would be 1. And so the relationship between Kp and Kc for this reaction would be Kp equals Kc times RT to the 1 power, which is just simply RT. And so if I gave you Kc, I could ask you to solve for Kp. If I gave you Kp, I could ask you to solve for Kc. And that's what this expression is useful for. Now, one thing we can say, though, is that if a reaction has the same number of moles of gas on the reactants and product side, well, in that case, delta N would be 0. It's not the case in our reaction, but if we had the same, like 2 and 2, or 1 and 1, or 0 and 0, so which typically we wouldn't use for Kp for, but in any one of those cases, delta N would be 0, and anything to the 0 power is 1. And if this all just comes out to 1 in such a case, well, then Kp would equal Kc. And so it turns out if you have no change in the number of moles of gas, that's when Kp will equal Kc. And that's worth remembering, because sometimes you'll be asked to do a calculation with something like this. They'll give you a reaction, and they'll either give you Kp or Kc and ask you to solve for the other one. However, more commonly than that is they'll just say, in which of the following reactions, A, B, C, D, E, would Kp equal Kc? And you're supposed to know that that means there's no change in the overall number of moles of gas for Kp to equal Kc. Now, one other thing to note about this is the value of R. Notice this RT here comes from PV equals nRT. And if you recall, we used 0.08206 liter atmospheres per mole Kelvin back in the chapter on gases, and that's the value of R you would plug in right here. This is important. So when you're dealing with like PV equals nRT type stuff with gases, this is typically the units for R and the value of R we use. When you're doing things in terms of energies, as we'll see later in this course, typically we use a slightly different value of R, 8.314 joules per mole Kelvin, because joules is a unit of energy. And so those are the two common values of R we present you with. And again, if you took a more advanced course in college called physical chemistry, we might just give you like 10 different values and you could pick your units, to whatever situation you're in, but we're not going to do that to you. That actually is not good to have so many options. So you get two options typically, two values of R. You get this one here, again, the liter atmospheres per mole Kelvin. Anything dealing with like the ideal gas law, PV equals nRT, and again, this comes from that, uses this value. Anything in the context of energy, which we'll see in a future chapter, we'll then use the 8.314 joules per mole Kelvin. And again, I will bring that up when we cross it later. So, but some of you guys are going to get an equation sheet, and you might have two different values of R on that equation sheet. I just want to make sure you know which one you need to use in this type of a calculation. One last point I want to bring out before we move on is that we call these equilibrium constants constants. So, and the big thing is they are constants. They don't change. Typically. There's one big thing that they will change for, and that's a change in temperature. If you change the temperature of a reaction, it will typically have its equilibrium constant value change. However, that's it. No, it doesn't matter what else you change. No matter what else you change, it does not change the equilibrium constant. You can change the pressure, doesn't change a thing. The equilibrium constant value will still be the same. You can actually change how much of the reactants or products are in your vessel, and it won't change the equilibrium constant. It just might take the system out of equilibrium, and it'll get back to equilibrium. And when it gets back, you'd find it has exactly the same value of the ratio of products to reactants raised to the power of the coefficients, the exact same value of the equilibrium constant. And so super important. Equilibrium constant, the only thing that will cause it to change in value is a change in temperature. All right, so one last set of comparisons we got to make with regard to equilibrium constants. And in this case, I'm going to give you a reaction. I'm giving you its equilibrium constant, and then I'm going to ask you for the equilibrium constants of three very similar and related reactions. And again, I can only ask you for the equilibrium constants because I've given you the equilibrium constant of this one above. Now, first thing I want us to do is write the equilibrium constant expression for this top reaction. In this case, we got Kc equals 278. And when I see it equals to 278, I probably think, well, there's probably more products than reactants. However, it's not excessively so. It's not bigger than 1,000, not bigger than 10 to the third. And so there still should be a fair amount of both reactants and products, but it is quite a bit bigger than 1 still, so not 1,000, but it's probably going to have more products than reactants, but not, again, excessively so. We wouldn't say that this favors the products or favors the reactants. We'd say that there's going to be both present at equilibrium. All right, so the expression here in this case is going to equal concentration of SO3 squared all over the concentration of SO2 squared times the concentration of O2. So products over reactants raised to the power of their coefficients. Okay, so that's our equilibrium constant. So the question then is, how does this reaction compare, the second one here, compare to the original that we know the equilibrium constant value for? Well, when you look at this reaction, you look at it, you see that the entire reaction is just switched around. Instead of having SO3 as the product, now SO3 is the reactant. Instead of having SO2 and O2 as the reactants, they're now the products. The whole reaction is flipped around. So, and if you notice that, once you get the trick here, you'll be able to quickly determine the equilibrium constant. But if we look at the equilibrium constant expression here for the second one, we can kind of see the difference. And so here it's going to be SO2 squared times O2 all over SO3 squared. And if you notice, that's just the inverse of this. Instead of having SO3 in the numerator, now it's in the denominator. Instead of having SO2 squared and O2 in the denominator, now it's in the numerator. And it's completely inverted. And so if the equilibrium constant for the top reaction equals 278, which is the same thing as 278 over 1, well, then if I invert the whole expression, then the equilibrium constant here should equal 1 over 278. And if we were to plug that into our handy-dandy calculator here, 1 divided by 278 is 0.0036. Cool. And again, I had to give you something that was at least some multiple, and we can, reverse it and stuff like that, but at least some multiple of the original reaction, or else we'd have no basis for comparison. So if we look at the next one here, I want you to give me the equilibrium constant of this one as well. And again, the key is, how does it compare to the original reaction? Well, when I look at it, SO2 is still reactant as well as O2, and SO3 is still a reactant, but all the coefficients are cut in half. Now, if you recall, I said earlier that the only thing that will change the value of an equilibrium constant is temperature. And here's where you can start an argument with me or your professor or instructor, and you can say, well, Chad, this is technically, whether you write it like this or like this, it's the same thing going on in your beaker. And that is true. However, we technically consider this a different reaction. And so it actually is not going to have the same numerical value of the equilibrium constant, it turns out, when you actually cut all the coefficients in half. If you look at the expression here, you're going to get SO3 all over SO2 times concentration of O2 to the 1/2 power. All right, so that's what you end up with. And if you compare this expression to this one up here, well, what do you need to do to turn this into this? Well, it's not divide by 2, not multiply by 1/2. You need to divide all the exponents by 2, multiply all the exponents by 1/2. And that's not the same thing as just simply multiplying by 1/2 or dividing by 2. So it turns out that would be the same thing as if you took this whole thing to the 1/2 power, which is the same thing as taking the square root. And so in this case, this is going to equal not 278, but 278 to the 1/2 power, the square root of 278. And if we plug that into our calculator, so square root of 278 is 16.67. I'll just round that to 17. Cool, so that's how that works. So notice if you cut all the coefficients in half, then you have to take the equilibrium constant to the 1/2 power. If you double all the coefficients, it would be to the 2 power. If you triple all the coefficients, you take the equilibrium constant to the 3 power. You'd cube it. So that's kind of how this works. So if we look at this last one, without even writing its expression, we can now take what we've learned above here and figure out what its equilibrium constant is going to be right from the get-go. How does this compare again to the original reaction? Well, it's reversed and cut in half. And if it's reversed, you got to do 1 over, the inverse. And if it's cut in half, you have to do the square root, the 1/2 power. Well, being reversed and cut in half, you have to do both. And it doesn't matter what order you do this in. You can do 1 over 278 to the 1/2 power, or you can do 1 over 278 all to the 1/2 power. That'll actually give you the same thing. So the order of operations here does not matter whatsoever. So in this case, I'm going to take that square root of 278, which we rounded to 17, but I'll leave it at 16.67333 something here. And then I'll do 1 over that answer and get 0.0599, so 0.060. Cool, and that's how that works. So, and again, this is another kind of question you could see showing up on a homework or an exam where they give you the equilibrium constant of one reaction and then ask the equilibrium constant value for some very related reaction. But it has to be for some related reaction. Cool, that is everything you need to know in principle about equilibrium constants. In the next lesson, we're going to talk about Le Chatelier's principle, much more conceptual in nature, but in the last 3 lessons of this chapter, they'll be very calculation intensive. Now, if you found this lesson helpful, would you consider giving me a like and a share? Pretty much the best thing you can do to make sure other students get to see this lesson as well. If you are looking for the study guide that goes with this lesson, if you're looking for practice problems, check out my premium course on chadsprep.com.